Good morning and welcome to class 15. Today we're going to cover sections 8.1 and 8.2, which deal with break-even analysis. The reading assignment is pages 222 to 233 in your text, and it covers sections 8.1 and 8.2. This instructor video, of course, will be on Blackboard, and you need to work as many problems as you can at the end of the chapter, as I always say. Break-even analysis in section 8.1 deals with a single project, and the basic equation to find a break-even analysis is given in equation 8.1, which says, excuse me, the break-even point is basically where the profit is equal to zero. So if you take the revenue minus the cost, that's the profit, set it equal to zero, and that is where you break even, when your profit's zero, okay? So if we have linear relationships with revenue and with cost, the total revenue R is equal to the revenue per unit, which is small r, this is capital R for total revenue, times the number of units, the quantity Q. And you can see that the revenue function starts at 0, 0. This is your quantity, Q, and this is your dollars or revenue or cost. And the total cost function, though, does not start at 0, 0. It starts here, a little bit up the scale, and this distance here is called the fixed cost. Okay, so you have the fixed cost, which is a constant number, plus then you have a variable cost. So the slope of this line is V, where V is equal to the variable cost per unit. So total cost is fixed cost plus V times Q. And so if we set the revenue equation equal to 0, then we want to find a point where the total revenue equals the total cost, because the cost is negative, and that would make that 0. And so that's what we do right here. This is total revenue R, which is little r times Q, and total cost is the fixed cost plus the variable cost per unit times the quantity Q. And if you solve that equation, you get the break-even point, QBE, which he says that's the quantity at which the revenue equals the cost, or you break even, is simply the fixed cost divided by the revenue per unit minus the cost per unit. Now certainly, since this revenue function starts at 0, 0, it must have a higher slope than the cost function, okay? The slope of this line here, the slope of the cost function line, is V. And the slope of the revenue function line is R, and it is a steeper slope than V, okay? And so equation 2 tells us that the break-even point is obtained by taking the fixed cost and simply dividing it by R minus V. An example of the application of that is the author gives us Nature's Pure Water vending company, and the water vending machine, the fixed cost is $900 per month per machine or per site, and the variable cost is 18 cents per gallon. The revenue per gallon is 30 cents per gallon, so that's your little r, that's your little v, that's your fixed cost. Your break-even point then is 7,500 gallons per month. We like to keep track now of the units, because like this is dollars per month, this fixed cost, and these are gallons, dollars per gallon, and so we will get dollars per month out of that. I'm sorry, just get dollars. I'm sorry, just get units per month. This is units per month. So let's this is gallons per month. Let's look at what the 900 is. 900 is dollars per month. Okay, and this number down here in the denominator is going to be 0.3 minus 0.818, which it will be 0.12, and that's going to be dollars per gallon. And when you divide that, the dollars will cancel and the gallons will go into the numerator because it's in the denominator of the denominator, so to speak. So that will give us 7,500 gallons per month, and that's the break-even point. So the author then says, what if the variable cost per unit is reduced through improved efficiency? What happens then? Well, he shows you in a graph here that if you reduce the slope of the variable cost line, your break-even point, of course, is going to be significantly reduced to a lower level. Again, if this number is smaller because it's a negative in the denominator, this number is going to be much smaller. So that pretty much covers this area. The author then asked, well, how much profit would you make per month if you sold 800 gallons? Remember from equation 8.1, the profit equals revenue minus total cost. And remember, total cost is fixed cost plus the variable cost per unit times the number of units. The revenue is simply the revenue per unit times the number of units. And so he sets that up, and then he plugs in 800 for the number of units per month. And when you crank through that equation, he gets $60 per month. Of course, maybe they have a lot of these out there, so they are making that level of profit. He says, what if the variable cost per gallon, V, could be reduced from 18 cents, which is what we had before, to 15 cents per gallon? And then he cranks through that equation and he says, wow, reducing that cost per gallon on the variable cost increases the profit significantly, even at that same level of 800 gallons per month sold. The next equation looks at the finding the cost per unit, and the cost per unit is simply the total cost divided by the number of units. That's simple enough. TC divided by Q, where Q is the number of units. Well, the total cost is the fixed cost plus the variable cost per unit times the number of units divided by Q. And so you can divide Q into the fixed cost, and then you just get plus V. And that's the total cost per unit. So, of course, the more and more units you produce, you're spreading that fixed cost over more and more units. You're reducing your total cost per unit, or your average cost, whichever you want to call it. And that's what equation 8.3 is pointing out. So the next section of the textbook deals with break even between two alternatives. That's section 8.2. And this is a very common type of problem. For example, here we have alternative 2 that has a higher fixed cost but a lower slope, so it has a lower variable cost, whereas alternative 1 has a lower fixed cost but a higher slope, so it has a higher variable cost. And this point where these two lines cross, where the total cost of alternative 1 equals the total cost of alternative 2, is called the break-even point between these two alternatives. So the concept is exactly the same, except when you're dealing with revenue and cost of revenue, always starts at 0, 0, at least for a linear revenue revenue function. So this is the section we're going to deal with now, and the author outlines a procedure for you, and the procedure starts with finding the common variable of interest. So you have these two alternatives, and you choose a variable of interest to do the break-even on. And then you're either going to use the annual worth or the present worth of these two alternatives to determine where the break-even point is. And so you either set the present worth of alternative 1 at the MAR equal to the present worth of alternative 2 at the MAR, or if you want to use annual worth, you set those two annual worths equal to one another, and then select the lower total cost alternative, and so on. Well, if you look at the figure that he's talking about there, or I'm talking about, is if, for example, this is your quantity, clearly the lower cost alternative is 1. But if this is your quantity, clearly the lower cost alternative is 2. So the alternative that has the higher fixed cost usually is better if you have a very high volume of quantity. The alternative that has the lower fixed cost is usually better at lower values of the Q variable, the quantity variable. So example 8.3 says Arrive Inc., a drone-based home service for food and packages, is considering one of 2 new drones. Use the estimates shown below and assume a 10% per year interest rate. Determine the minimum number of deliveries to justify the higher cost of the drone, and then comment on the feasibility of this solution relative to each drone's delivery capacity. If there are 6 operating hours per day and 200 operating days per year. So the number of hours per year then would be 6 times 200, 1,200 hours per year of deliveries. So he calls it the Inspira alternative and the Rapida alternative. The Inspira costs quite a bit more. It has a present cost of $230,000. It has a salvage value of $40,000. It will last 8 years. Has annual operating cost of $30,000 and annual salary of $40 per hour for the operator, and only one operator is required, and it can make 6 deliveries per hour. The lower costing alternative, Rapida, has a first cost of $80,000. It has no salvage value. It'll only last 4 years. And the annual operating cost is $15,000 for the drone itself, but the labor cost is $30 per hour times two operators to maintain the operation of this particular drone, and it'll only deliver 5 packages per year. And so the author says find the break-even point if the interest rate's 10%, and how many deliveries would you have to make per year between these two alternatives. So we'll go on to look at that example a little further. Go through the steps that we outlined before. First thing is determine the variable of interest, and then set up an annual worth equation. The annual worth makes more sense in this case because this particular alternative only lasts 4 years, so you're going to have to repeat that cash flow. But that's what you're going to assume, that you can. We're going to assume an 8-year planning horizon, which is the least common multiple of lives. We're going to assume that this can be repeated, so that the annual cost for 4 years will be exactly the same as the annual cost for 8 years. That's kind of an implicit assumption we have to make when we have two different alternatives that last different life lengths, that have different end values. Okay, so the variable cost relationship for alternative one is you've got $40 per hour, and that's the labor rate, but you make 6 deliveries per hour. So if you divide by that, you get this relationship. You're basically dividing $40 per hour by 6 deliveries per hour to get dollars per delivery, and then you multiply it by deliveries. Deliveries per year will give you dollars per year. So it's 40 divided by 6 is 6.67. That's $6.67 per delivery times D deliveries per year will give us dollars per year. And then the this is the Inspiron drone, Inspira, and then here's the Rapida drone. It's $30 an hour, but there's 2 people, so you have to multiply by 2, and then you have divide that by 5 deliveries per hour. So times D deliveries per year, and you get 12D per year for the variable cost of the Rapida option. And then you set the annual worths of these two things equal to one another. Recall that the price of the Inspira drone was $230,000, and it lasted 8 years at 8%. I'm sorry, at 10%. But it has a salvage value of $40,000. So your annual cost of that owning that drone is equal to, if you do the math with this and this, you come up with minus $35,000, and then you add the variable cost, 6.67 times D, and this is going to be dollars per year then. Okay, this will be dollars times spread over so many years, over in fact 8 years will give you dollars per year. This will give you dollars per year, and this will give you the relationship. And so oh, I'm sorry, this minus 35,000 came from this operating cost. And so this is the investment cost, this is the operating cost, and this is additional operating cost to make the deliveries. You do all the math on that, and you get minus 74,614 minus 6.67D. If you do the same thing for the other alternative, it costs $80,000 but only lasts 4 years, has no salvage value, has operating costs of $15,000 a year, and then 12D was the variable cost there. So you do the A given P, 10% for 4 years, you get a number, you add that to the minus $15,000 per year, and you get minus 40,238. So what that means is that this must be minus 25,238. When I add that to the minus 15, I get the minus 40, and then I add in the minus 12D. And so you equate those two together and you solve, and you get D equals 6,400 deliveries per year is your break-even point. You can see that this one has a higher fixed cost, but lower cost per unit, whereas which a unit is a delivery. This has a lower fixed cost but a higher cost per unit. So so we have a graph that will look like something like this, and I'm going to turn this, those are negative, I'm going to multiply them all by minus 1, and so I have 74,614 with a slope of 6.67, and then I have 40,238 with a slope of 12, and we found out that they will cross at 6,450 for our quantity. These are dollars. So that's what this thing looks like. And if you break that down into deliveries per hour by dividing by the number of hours per year, remember it was 6 hours a day, 200 days a year, so we got 1,200 hours per year of operation, you get 5.38 hours deliveries per hour. If we, this is deliveries per year. If you break that down to deliveries per hour, it's 5.38 deliveries per hour. And so the author draws that up for you here. Okay. Conclusion: choose the Inspira drone if more than 6,450 deliveries per year, or 5.38 per hour, and then that plots it out for you. And that is the conclusion of today's lecture on sections 8.2 and 8.1. Thank you.